Yeah, great. So we have discussed all the mean value theorems, Rolle's theorem, Lagrange's mean value theorem, Cauchy's mean value theorem, and along with that, so we have given the proofs for the Taylor's expansion and the Maclaurin's expansion. So which is an extension from the Lagrange's mean value theorem, right? Then based on that understanding, we will be solving certain problems today. So once we are done with that, then we can move on to the next topic. Now here, so note down one problem. Verify Rolle's theorem in the case of verify Rolle's theorem for f of x is equal to x minus a whole power m into x minus b whole power m. Can you verify Rolle's theorem on this? Anybody got the answer for this? Yeah, so this is a polynomial function. Then this function, the function is continuous. So the verification is in between a comma b. The function is continuous between a comma b and differentiable between a comma b and, so this is continuous and differentiable. All the polynomials are continuous and differentiable over the real range, right? So over the real range. So this is continuous and differential function, and f of a is equal to 0 and this is equal to f of b. So all the conditions of Rolle's theorem are satisfied. Rolle's theorem are satisfied. So as per Rolle's theorem, and there exists a value c in between a and b such that f dash of c is equal to 0. So here the given function is f of x is equal to x minus a whole power m into x minus b whole power n. Now the derivative of that is f dash of x is equal to, so that is m into x minus a whole power m minus 1 into x minus b whole power n plus x, so n into x minus b whole power n minus 1 into x minus a whole power n, right? So this is the derivative of the function. Now from this, if you take x minus a whole power m minus 1 into x minus b whole power n minus 1, if you take it out, then this will be, so okay, so you can do this, I think. So from this actually, so this is equal to 0. Then find the value of x by taking this condition. Can you solve it and then tell me? I hope you should be able to do that. Yeah, yes, that's exactly. So can somebody confirm, Prithvi? mb plus na by m plus n. Yeah, great. So this is simply take x minus a whole power m minus n and x minus b n minus 1, then try to equate to 0, and this factor, whatever you took it common, will be 0, and the rest of the part, if you simplify it, you are going to get the value. So what Prithvi gave it? That is x is equal to mb plus na by m plus n. So this is nothing but the arithmetic or weighted arithmetic mean of a and b. So this will be definitely, this is in between a and b, right? So this is division of AB length into the ratio of m is to n internally, which essentially means that internally this point lies. So as per Rolle's theorem, there exists a point such that wherein f dash of c is equal to 0, and that c value is mb plus na by m plus n, and this is in between a and b. Got it? This is how we will be proving the Rolle's theorem. Clear? Or do you have any questions on this? Anybody? Note down one more. Verify Rolle's theorem. Verify Rolle's theorem. F of x is equal to e power x into sin x minus cos x between pi by 4 comma 5 pi by 4. So first verify the conditions of Rolle's theorem, and then try to prove that the Rolle's theorem is valid within this range for the function f of x is equal to e power x into sin x minus cos x. So this is straightforward and easier. So you can solve it on your own. So if you are not able to solve, I am going to solve it for you. So this is an exponential and trigonometric function. It is again continuous and differentiable function. So it is in between the real range. So what you need to verify is verify the function value f of pi by 4 and f of pi by 4 both should come as 0. Then all the conditions of Rolle's theorem are satisfied. Then you can identify f dash of x which is equal to 0, and then get the values of x, which is nothing but the c value in between a and b. Got it? So f of pi by 4 is equal to f of pi by 4 is equal to 0. So because pi by 4, sin pi by 4 minus cos pi by 4, both are 1 by root 2. So both will become 0. And then 5 pi by 4, both will in the third quadrant. So sin pi by 4 will be minus of 1 by root 2, and cos pi by 4 will be minus of 1 by root 2. So this is again 0, right? So once you identify the conditions of Rolle's theorem, then f dash you can find it out. So f dash of x is nothing but e power x into derivative of sin x is cos x minus derivative of cos x is minus sin x plus sin x minus cos x into derivative of e power x is again e power x, and this is equal to 0 as per Rolle's theorem. Then this is e power x, you can take it common and take it to 0. Then this will be cos x plus sin x minus cos x is equal to 0. Then this will cancel out. Then 2 sin x is equal to 0 or sin x is equal to 0 simply. And the general solution of x will be so n pi, where n is in between 0, 1, 2, 3, 4 plus or minus, right? So all the values of n will satisfy within the whole, so within the natural number, within the integer numbers from minus infinite to plus infinite. So you can take any value in between pi by 4 and 5 pi by 4. These values are, one is 0, another is pi, and 2 pi, 3 pi on the positive range. Anyway, we need only on the positive range, that is in between pi by 4 and 5 pi by 4. So there are values, that is only one value, pi is there, right? So obviously C is equal to pi is the solution. Got it? So I hope everybody got the answer for this. Yeah, this is straightforward and easier. Verify Cauchy's mean value theorem. Verify Cauchy's mean value theorem for the functions x square and x cube. X square and x cube in the interval 1, 2. Can you verify Cauchy's mean value theorem on this? These are polynomial functions. So both are continuous and differentiable within any given range of real numbers. And here he has given 1, 2 as a real range, wherein the function is continuous and differentiable between 1, 2. Then, as per Cauchy's mean value theorem, so f of 2 minus f of 1 divided by g of 2 minus g of 1 is equal to, so this should be f dash of c divided by g dash of c, where c is in between a comma b. So this is Cauchy's mean value theorem. And here f of x is x square and g of x is x cube. So you can take any one. So that's not a big deal, right? So f of x is equal to x square and g of x is x cube. Then identify the values. So also you can take the derivative of this. This is f dash is equal to 2x and g dash is equal to 3x square. Then this range will be 2x divided by 3x square. These two will cancel, 2 by 3x. So at c, so this will be 2 by 3c. And this value on the left side, f of 2 square will be 4 minus 1 square will be 1. And then 2 cube is 8 minus 1. And this is equal to 2 by 3c. So this comes out to be 3 by 7 is equal to 2 by 3c. It implies c is equal to 9 by 14. So this is the value of c. 9 by 14 will definitely be in between it's not in between, right? Yeah, sorry. This is 1 by c, not. Yeah. So c is equal to 14 by 9. This is equal to in between 1, 2. Got it? Yeah. So got it? So here actually this is one kind of case wherein verification of the theorems, the fundamental theorems, maybe Rolle's theorem, maybe Lagrange's mean value theorem, and maybe Cauchy's mean value theorem. So this is the verification case. But most of the times, so he will end up asking the reminders. So actually we are going to deal certain problems based on reminders. Note it down. See this, these are all the kind of models what we are going to discuss it. So there is a possibility of asking the questions in the first question or the fifth question, wherein definite questions. So there is a possibility of asking this level of questions also. These are easier only, but most of the times actually the questions will be asked on the reminders. Got it, Anjali? But for the sake of completeness, we should be covering everything. Yeah. Prove that prove that 0 less than a less than b less than 1, 0 less than a less than b less than 1, b minus a by 1 plus b square b minus a by 1 plus b square is less than tan inverse b minus tan inverse a is less than b minus a by 1 plus a square hence show that pi by 4 plus 3 by 25 is less than tan inverse 4 by 3 is less than pi by 4 plus 1 by 6. Can you prove this? So this kind of questions can be asked. So that you need to guess. Raj. So f of x is not given. How can you assume f of a and f of b? So first you have to be aware of what is f, right? So this is the question from the Lagrange's mean value theorem. So there is no question of integration. So here you need to intelligently guess. So here actually Lagrange's mean value theorem for any random function. So it will be f of b minus f of a divided by b minus a. If you bring this b minus a here, f of b minus f of a divided by b minus a format, that is in between, which essentially means that f of x you can assume as let f of x is equal to tan inverse of x. So this is the intelligent guess you need to make it based on the function what is he has given, right? Then rest of the things within between a comma b. So then it is simply applying Lagrange's mean value theorem. Got it? Yeah. Raj, see this. If you bring this b minus a here, it will be f of b minus f of a divided by b minus a format, where f can be tan inverse of x. Got it? That is a guess that you have to guess it. Understood, Raj? Yeah. So from this, so exactly the same procedure what we have adapted. So then it will be in between f of b. So as per Lagrange's mean value theorem, so f dash of c is equal to f of b minus f of a divided by b minus a. So this is as per Lagrange's mean value theorem, and in between a, c, b. Got it? So then actually what you can consider is, so a less than c less than b. So but the derivative of f, so f of x is equal to tan inverse of x. It implies f dash of x is equal to 1 by 1 plus x square. So this is when x is equal to c, then this will be 1 by 1 plus c square. And the condition is a less than c less than b, right? So then a less than c less than b. If you square it, it will be a square less than c square less than b square. And if you add 1 plus 1 plus 1 plus, so there won't be any change in the sign. So which essentially means that 1 plus a square is less than 1 plus c square is less than 1 plus b square. If you take the inverse of it, this is 1 by 1 plus a square. Now less than will become greater than because you are inverting the function. So this is 1 by 1 plus c square is greater than 1 by 1 plus b square. Got it? So if you take it to the other side, if you want to keep the less than sign, then you can keep, so you can interchange this one and change the sign. So 1 by 1 plus b square is less than 1 by 1 plus c square is less than 1 by 1 plus a square. So greater than became less than, and these two are interchanging. So there won't be any functional difference between these values. Got it? Understood or not? And as per Lagrange's mean value theorem, 1 by 1 plus c square is equal to tan inverse of b minus tan inverse of a divided by b minus a. So this is as per Lagrange's mean value theorem, and I have brought this format. So then you can replace that point here. Then 1 by 1 plus b square is less than tan inverse of b minus tan inverse of a divided by b minus a is less than 1 by 1 plus a square. So this b minus a you can take to the other side. So this is what he asked us to prove. Got it? Any questions on this? So essentially, in this case of problems, what we are doing is, so we need to guess the function. That is one thing you need to do. Another thing is, take the conditions of C and then try to bring in the format of the middle part, that is the derivative part. So for that you will essentially use the same condition, that is A less than C less than B, and this condition you will make use to bring into the format of the derivative, and then based on that, whatever the conditions he asks for, that you are going to check it. So this is the methodology that we are going to adopt in this kind of cases. Clear? A less than C less than B, exactly. Any questions? So Keshav, you are asking me to review this again? So just what we are doing is, see this, here actually prove that 0 less than A less than B less than is less than 1 is the given condition. That means A, B values are in between 0 and 1, right? A, B values, both the values. Here actually, essentially what he is trying to say is, forget about the Rolle's theorem and talk about only the Lagrange's mean value theorem, because within the range of 0 to 1, so there is no possibility of the function tan to have the value of between, so making the same value for A and B. So that is continuously increasing function. That's why he has given this condition. And then the second part is b minus a by 1 plus b square. Tan inverse b minus tan inverse a is less than b minus a by 1 plus a square. So this is what he asked us to prove. But here actually he didn't mention about the function. For that you need to guess the function based on the condition what he has asked for. So this condition is, he asked for tan inverse b minus tan inverse a. And then here you can find one b minus a. Here you can find one b minus a. Then if you bring this to far here, then this is as if like f of b minus f of a divided by b minus a. So this format is here where in the place of f there will be tan inverse of x. So this tan inverse x we need to catch there. So once you got that, then f of x is equal to tan inverse x. You can apply Lagrange's mean value theorem between a and b. So this Lagrange's mean value theorem is finding out the derivative. So anyway, we are aware of A less than C less than B. This is a fundamental condition for the Lagrange's or Rolle's theorem, or even the Cauchy's mean value theorem also. Hence, once you identify this condition, take the derivative of it. That is coming as 1 by 1 plus x square, and at x is equal to c, this is 1 by 1 plus c square. So you need to bring into this format this condition. For that, I am taking step by step. So A less than C less than B, and for that I have squared it, because at the denominator there is c square. Now I have got the c square from c. Then I have added 1 on all the sides, so that I got this format 1 plus c square. Then I inverting that function, because I need 1 by 1 plus c square. So 1 by 1 plus a square is greater than 1 by 1 plus c square is greater than 1 by 1 plus b square. But here, if you notice, this greater than symbol is inverted to less than. Sorry, less than symbol is inverted to greater than symbol, because you are inverting the function. So there are only two cases where the less than become greater than and greater than become less than. Those two cases are, one is if you are making this to the denominator, then there is a possibility of making this to the invert. If you are multiplying this entire equation with a negative sign, again there is a possibility of inverting this sign. So that is greater than become less than, and less than will become greater than. These are the two possible conditions while you are making these conditions. Got it? So if you are inverting, change the sign. So 1 by 1 plus a square is greater than 1 by 1 plus c square is greater than 1 by 1 plus b square. But in the original condition, b square is here and the other side is a square. So that's why what I will do is I am inverting these locations from here to here and here to here. So that is again 1 by 1 plus b square, 1 by 1 plus c square, 1 by 1 plus a square. But again I inverted these signs because I interchanged the locations. So without making any change in the definitions, we are making all these things. Now once you got this, then what you can replace is 1 by 1 plus c square. Anyway I got this. This value as per Lagrange's mean value theorem, this is f of b minus f of a by b minus a. That is nothing but tan inverse of b minus tan inverse a by b minus a. I can bring it straight away at this location. And then once I got at this location b minus a, I will take it to both sides, so that my required condition is met. Got it? Any questions? Okay. So yeah, great. So once you arrive at this, then the second question is, he asked for pi by 3 is less than pi by 4 plus 3 by 25 is less than tan inverse of 4 by 3. So how to prove this? And hence prove that. So from this condition we will be proving that. Can you tell me how can we do this? See this. So this pi by 4 is nothing but tan inverse of 1. So that anybody can guess it. So but here actually out of tan b minus tan inverse b minus tan inverse a, one part is missing. So that part could be tan inverse of 1, because the pi by 4 is on both sides. This is nothing but tan inverse of 1. If you bring it to this side, then this will be tan inverse of 4 by 3 minus tan inverse of 1. So here in this equation, if a is equal to 1 and b is equal to 4 by 3, so these are the conditions you need to guess it. So if a is equal to 1 and b is equal to 4 by 3, then you can identify this relation by substituting it here. Got it? So here actually the conditions what we proved is 0 to 1, right? But here actually that is still valid even to the upper sides as well. Got it or not? Above 45 degrees also is valid. So that's why you can apply even here as well. Got it, Raj? We tried checking in between these two, but it is still valid further also. That is, if you notice 1 and 4 by 3, that is above 1. So this is valid till infinite on the positive side. It's not crossing the negative or more than 90 degrees. That's the reason you can still apply it. Okay. So any other questions? Prove that log of 1 plus x log of 1 plus x is equal to x by 1 plus x theta. Where 0 less than theta less than 1, and hence deduce that x by 1 plus x is less than log of 1 plus x is less than x. And x greater than 0. Right? Okay. So can you prove this? Here actually prove that log of 1 plus x is equal to x by 1 plus x theta, where 0 less than theta less than x, and hence deduce that x by 1 plus x is less than log of 1 plus x is less than x. Can you prove that? I'll give you 2 minutes time, so you can try to solve on your own. So A is not 1. So this is a form of Maclaurin series. So Lagrange's form, extension to Maclaurin series, right? So you know that f of a plus h is equal to f of a plus h into f dash of a plus h theta. And this is what is the Lagrange's mean value theorem in remainder format, right? The same thing we extended as the Taylor's expansion. And then from Taylor's expansion, we brought the Maclaurin's expansion by taking a is always 0 and h is always x. That is the assumption we made, right? So even at the Lagrange's mean value theorem also, you can assume a is equal to 0 and h is equal to x. So this is as if like expanding within the range from 0 to x. So if you start from 0, then any value, if you are taking on left side or right side, it is always x, right? So obviously, if you take one more point, b is equal to x and a is equal to 0, obviously h is equal to b minus a is again equal to x. So this is Lagrange's mean value theorem expanded in between 0 and x for any random function. That random function is log of 1 plus x. Clear? Akhil? Yeah. So with this assumption, you will be able to prove that easily. Exactly the same procedure what we have done in the previous problem. Now let me solve it. See this, f of a plus h is equal to f of a plus h into f dash of a plus h theta. So if we apply Lagrange's mean value theorem, between 0 comma x, then the remainder form of Lagrange's mean value theorem will be f of x is equal to f of 0 plus x into f dash of 0 plus x theta. And this is f of 0 plus x into f dash of x theta. And this is the value of f of x, where f of x is equal to log of 1 plus x, right? Obviously, f dash of x is equal to 1 by 1 plus x. So that is the f dash of x. Now here, f of 0. So f of 0 is log of 1 plus 0 will be log 1, and log 1 is anyway 0. So here, f of x is equal to x into f dash of x theta. Got it? So it implies f of x is equal to log of 1 plus x is equal to, so x into f dash of x is 1 by 1 plus x, and f dash of x theta will be, so 1 by 1 plus x theta, which implies that log 1 plus x can be expressed as x by 1 plus x theta, where 0 less than theta less than 1. So this is as per Lagrange's mean value theorem in theta format, right? I hope you are aware of it. Right? So you are saying that, so x is equal to 1, right? So you are trying to get it in between 1 and x. So this is what you are trying to do. Got it? Okay. So I think so you may get the answer, because we are trying to apply between any two different limits. But this is most easiest what we are solving it here. So if you take one limit as 0, straightforwardly your calculations will be simple. But if you keep as 1 to theta, 1 to x, then it will be in between. Always you need to carry log 2 everywhere. Got it? Yeah. So from this, so this is the value of log 1 plus x. It will be x by 1 plus x theta. So once you got this value, from this condition, try to get this value. Then you will be able to get the condition of x by 1 plus, so x by 1 plus x is less than log of 1 plus x is less than x. Got it? Okay. So you try on your own. 0 less than theta less than 1 should be brought into the format of this format. So this can be replaced with this one while taking the conversion from 0 to log 1 plus x. So this is 0 less than theta less than 1. Multiply x on either side. 0 less than x theta less than 1 is x theta less than x. Then add on either sides 1. So 1 less than 1 plus x theta less than x plus 1. Then take the inverse of it and reverse the sign. So less than will become greater than. Then you will get this format. Then again multiply with x. You are going to arrive at this condition. Clear? Understood or not? So log 1 plus x is equal to x by 1 plus x theta. So this is what we got it, right? Yeah, that's correct. So 0 less than theta less than 1. Now I will multiply x on either side. Then I will add 1. Then I will take inverse. Then I will multiply x. Then I will write this here and this one the other side. So x by 1 plus x is less than x by 1 plus x theta is less than x. And this I will replace with the original function of log 1 plus x. So x is x by 1 plus x is less than log 1 plus x is less than x. So this is the condition he asked us to prove. Got it? Great. I think so. These are all the kinds of models you can think of. So I'll give you one last problem. f of x is equal to log 1 plus x, comma x greater than 0. So x value is always greater than 0. Using Maclaurin's theorem, show that for 0 less than theta less than 1, for 0 less than theta less than 1, log 1 plus x is equal to x minus x square by 2 plus x cube by 3 into 1 plus x theta whole cube, and hence deduce that log 1 plus x is less than x minus x square by 2 plus x cube by 3. Yeah, can you prove this? So this is Lagrange's mean value theorem in the remainder format. So here f of x is given as log 1 plus x. Then f dash of x is equal to 1 by 1 plus x, and f double dash of x is equal to, so this is minus 1 by 1 plus x whole square. Then f triple dash of x is equal to 2 by 1 plus x whole cube. So this is the derivatives correspondingly. Then it implies f of 0 is equal to log 1 is equal to 0, and f dash of 0 is equal to 1 by 1 plus 0 is 1, and f double dash of 0, this is minus 1 by 1 plus 0 whole square, this is minus 1, and f triple dash of 0 is 2 by 1 plus 0 whole cube, this is plus 2. So this is the coefficients of Lagrange's mean value, the coefficient of Maclaurin series. Now the Maclaurin series can be expanded as f of x is equal to, so f of 0 plus h into f dash of x, f dash of 0 plus, sorry, x into x square by 2 factorial into f double dash of 0 plus x cube by 3 factorial into f triple dash of 0. So like this, actually you can expand till the nth derivative, right? Now if you want to keep it here itself, so that is x theta, you have to keep it. This is in the remainder format. Got it? I hope everybody is aware of that Maclaurin series. Clear? Now correspondingly replace these values there. Got it? So f of 0 is anyway 0, and then x into f dash of 0 is 1, and f double dash of 0 is minus 1, and f triple dash is 2 plus 2, right? So here if you expand it, I hope you noted down. Can I erase this? Is it noted? Yeah. So, and these values, so f of x, that is log 1 plus x, can be expanded as f of 0 is 0, and then x into f dash of 0 is 1, and then minus x square by 2 plus x cube by, so 3 factorial, that is 3 into 2 into, so f triple dash of 0. So this is one plus x theta whole cube. You can keep it like this, I think. So you don't need to substitute this. This you can keep it whole cube. Yeah. So this is as it is, you can keep it. So into 2 will be there. So this 2 will cancel. In the remainder format, x minus x square by 2 plus x cube by 3 into 1 plus x theta whole cube. So this is log 1 plus x format using the Maclaurin's expansion in the remainder format. So in the remainder format, you notice that this theta will be there. And the given condition is, there is a condition what he has given is, that is x greater than 0 and theta is also greater than 0. So these two we know. So but we need this factor 1 plus x theta. So that's why if you multiply x theta, this will be greater than 0. So if you add 1 on either sides, then 1 plus x theta is greater than 1. And then inverse of that, because this is at the denominator, 1 by 1 plus x theta is less than 1. If you cube it on either sides, this will be 1 by 1 plus x theta whole cube is less than 1. Now, if you multiply with x cube on either sides, this is x cube, this is x cube. So, x cube by 1 plus x theta whole cube is always less than x cube. This is proved. Got it? This is proved. From this, you can replace it here. See this. And hence deduce that log of 1 plus x is less than x minus x square by 2, x cube by 3. Now here, so if I divide with 3 here, and there will be 3 here. Now in the expansion of log 1 plus x, x minus x square by 2 plus x cube by 3 into 1 plus x theta whole cube. And then this format we can bring in this. So by adding minus x square by 2 and plus x. So if you add that, that is x cube by 3 into 1 plus x theta whole cube is less than x cube by 3. Now I add minus x square on either sides, and then I add plus x on either sides. Then it will be this side x minus x square by 2 plus x cube by 3 into 1 plus x theta whole cube. This entire thing I can replace with log 1 plus x, and this is less than x minus x square by 2 plus x cube by 3. Clear? Understood? Anybody wanted me to repeat? I hope everything is perfect. And these are all the kind of models you can expect. So all these are standard models. Yeah. So that may be asked based on the Lagrange's mean value theorem, Cauchy's mean value theorem, or Rolle's theorem. Just to prove the Rolle's theorem or Lagrange's mean value theorem or the Cauchy's mean value theorem. That is one method. Another method is, that is finding the approximate values based on the conditions. So this is maybe based on the Lagrange's mean value theorem, or maybe based on the Maclaurin series or Taylor series. It will be exactly the same thing. Only difference will be, if it is Maclaurin series, you will take the starting point as 0. If it is a Taylor's expansion, you can take any value as the starting point as randomly here. So that's the only difference. But entire procedure is same. But only intelligence where you need is to identify the appropriate function. That is one case. And another case is from the given conditions, you have to bring whatever you need. So that is taking these conditions and proving to the extent whatever you need. So this is another thing. So where you need a little bit of intelligence. So rest of the things is hard and fast rules, nothing more than that. Clear? Okay. So with this, I would like to stop the class for today. So this concludes our topic of mean value theorems. Then we'll go to the other things. Got it? So in the next class, I'll take up a new topic.